Now let me introduce you to geopolymerization, a revolutionary process in the material science that offer a sustainable alternative to traditional cement. Geopolymers are inorganic and eco-friendly materials with unique properties which we will explore in this presentation. Let's dive into what makes geopolymers so special, illustrating their compositions and their properties. Now, coming to the geopolymers are made from aluminosilicate material rich in silica and alumina. Common raw materials include fly ash, a byproduct of coal combustion, slag from steel production, metakaolin derived from clay, and red mud, a residue from aluminium processing. These materials are abundant, often considered industrial waste, making geopolymerization a sustainable choice by repurposing byproduct. Now, to transform these raw materials into geopolymers, we use chemical activators. The most common activators are alkaline solution, such as sodium hydroxide or potassium hydroxide, often combined with sodium or potassium silicates. These activators trigger the geopolymerization reaction, bonding the silica and alumina into a strong, durable matrix. This process is to key in achieving the material's unique property. Fly ash is a cornerstone of geopolymer production due to its high silica and alumina content. These two components are having got a tremendous role. When mixed with the activators, fly ash undergoes a chemical reaction that forms a robust geopolymer network. This process leaves the abundant availability of fly ash, turning waste into a valuable resource. However, the composition of fly ash can vary, so careful selection and testing are essential to ensure consistent result. The geopolymerization process yields a hard stone-like material with exceptional characteristics. Geopolymers are as strong as traditional cement, highly heat resistant, and incredibly durable, making them ideal for demanding applications. Best of all, they produce significantly less CO2 during production, making them a greener alternative to conventional cement, reducing the environmental footprint of construction. Unlike ordinary Portland cement, which rely on high temperature clinker production, geopolymers use industrial byproducts and a low energy chemical reaction. This results in a lower carbon footprint as geopolymer produce its production emits up to 60 to 80% less CO2. Additionally, geopolymers offer a superior resistance to chemical and high temperature, making them more versatile for a specialized application compared to the traditional cements. So, geopolymers are used in a wide range of applications from construction to infrastructure. They are employed in precast concrete production, road pavements, and even fire resistance coating due to their heat resistance. Geopolymers are also used in waste uh, encapsulation, helping to immobilize hazardous materials safely. Their versatility and eco-friendly nature make them a go-to material for sustainable building projects. Now, as you can see in this slide, that there is a typical comparison between ordinary Portland cement and geopolymer cement, and as we can see that two rows has been marked. One is CO2 emission part. Here you can see that geopolymer having got a lot of CO2 emission saving, and as for the market cost is concerned, also this geopolymer are superior. Now, coming to the some key differences, especially raw materials and other part, it's almost similar, but few things which are important. That is the key product formation. As we can see that in ordinary Portland cement, CSH, that is calcium silicate hydrate gel, is in action, and in geopolymer cement, NASH, that is sodium aluminosilicate hydrate gel, is in activities. So, so we can say that this is also a very informative slide. Now coming to the this slide, it is also a similar characteristic comparisons of both conventional and geopolymer cements. And here we can say that um, it's also a sort of a comparison altogether. What sort of fire resistance is there, what is the time lifespan, and mostly we can see that and here in almost all summary, geopolymer cements are far more looks far more superior in almost all respect, we can say. Mm. And as for one important test for geopolymer measuring is carbonation depth. Carbonation depth we can see, and the last note number 16, serial number 16 is the carbonation depth, which indicate how will the material resist carbon dioxide penetration over time. Typically, after 28 to 56 days, polymer shows a carbonation depth of 5 to 10 millimeters, demonstrating excellent durability. This low penetration rate ensures the material remains strong and resistance to degradation in harsh environment. So we can say that it is one of the most important characteristic that need to be evaluated. Mm. Now coming to the most important part is rapid chlorine permeability test. That is a key test which measure how much electric charge passes through a geopolymer sample, typically period like uh, over a period like suppose 1996 coulombs. This test assesses the material's resistance to chlorine ion penetration, which is crucial for structures exposed to salt water over de-icing salt, such as bridges or coastal building. Lower permeability indicate lower permeability indicate better durability. So we can say that the results from the test like carbonation depth and chlorine permeability tells us how geopolymer perform under environmental stress. Low carbonation depth and chlorine permeability indicate that geopolymers are highly resistant to corrosion and degradation, making them ideal for long-lasting infrastructure. These results confirm that geopolymers can outperform traditional cement in many scenarios, especially where durability is a critical aspect. Now coming to the geopolymers importance, and that cannot be underestimated. They are really important because of they address two major challenges in construction. One is the sustainability that we have seen, and the performances, and we have compared almost each aspects of the performance. And we can say that by reducing CO2 emission, they help combat climate change. With their strength, heat resistance, and durability, make them suitable for demanding application. And hence, geopolymers represent a step towards greener, more resilient infrastructure, aiming with a global effort to build sustainability. To conclude, geopolymers offers a sustainable, high-performance alternative to traditional cement by utilizing industrial byproduct, reducing emission, and providing superior durability. Geopolymers are paving the way for eco-friendly construction.